right. Oh, I think we are live. Are we live? Yes. Okay. Just let me pull up this thing to figure out the comments again, of course. But yeah, it's good to be back. I need to turn off the sound. Welcome to live chat. All right. Sick. Cool. Yeah. If you can hear me, type something into the chat so that I can see that. Not just that you can hear me, but also that that the chat works. All right. Yeah. Hello and welcome to another session of open source type level cats, whatever. Happy to do this again. And I don't really have a script or anything today. But something I would like to do on that Jakub talked to me about yesterday. Not talked to me about. He complained about not having complained is not the right word, but he was like, oh, we should have this in cats. And what he wanted is a Haskell type class called decidable. So let's have a look at that one. Oh, I should probably specify that. Let's see. So there's divisible, which I believe is, yes, that is contravariant duplicative. And then we have contravariant alternative, which is decidable. So we already have this divisible type class. In cats, it's called contravariant monoidal, which I don't know, maybe not the best name, but I think it gives a very clear picture of what it is, which is a monoidal and it's contravariant. And the way to see it is, like, if we look at this method, and apologies for those that don't know how to read Haskell, basically this is a function called divide. It takes a function from some a to a tuple of b and c, and then an f of b and an f of c, and then returns an f of a. And this is kind of like if you flip all the functions around, all the arrows around, right? That's when you get applicative, right? So if in an applicative sense, basically you would go from b and c to a. So yeah, so I should have said you don't flip around all the arrows, but you flip around this arrow inside here. I guess you could flip around the other arrows too. I don't know. But yeah, so instead of going from a tuple to a single thing, you go from a single thing to the tuple. And then conquer is kind of like the pendant to pure. And we can see why this is just an f of a. So this looks more like the monoid empty. But in a second I will show you why. Let's first look at decidable. So decidable is very much like alternative. Alternative, for those that don't know, is basically applicative plus monoid k. And divisible is kind of the same, where you'd kind of like have these two different things. To do two different, I want to say monoids. So you have like choose, and then you have divide. And choose is basically the same thing, just except of this tuple right here, tuple b and c, you have a an either bc, right? And for those that were here, I don't know if it was last time or 2 times ago, those things are like dual to each other, either and tuple, or products and coproducts, or products and sums. And I kind of forgot where I was going, but yeah, So this is the same thing as divide, 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 yeah, except for the either, and in the same way, combine K is the same thing as map 2, just instead of either you have a tuple, kind of. So it's not map 2, it would be tupled or whatever. I think it's called product in cats. So this is like a brief, scrappy introduction. So let's look at how this actually looks in cats. So in cats, the thing first of all we have is semigroupal. And semigroupal basically just defines this product method that says that if I have an f of a and an f of b, I can get an f of tuple ab. And then commonly that is extended by apply, which then gives us map 2, because, right, so if you think about it, if you had an f of a and an f of b and a function from a to b to some type z or z, and you had a semigroupal and a functor, that basically gives you map 2, right? And that's exactly what it is. You go product, and then you map over it, and then you basically apply this f to this tuple, and this tuple just turns a function of arity 2 into function of arity 1 that takes a tuple. So I guess this is uncurried? Is this uncurried? Yeah, something like that. Right, and so if you look at apply, it actually extends functor and semigroupal, but not semigroupal, it extends invariant semigroupal, and that is because, for those that don't know, functor, oh no, my IDE isn't working, that's not good. I'm gonna try to import the build, hope that works in time. Yeah, so functor actually extends invariant, and invariant is just a different kind of functor where you basically have a type constructor that is where it's, how do you even call it, where its type member is itself invariant, right? So functor for something like list is a covariant type, therefore you can have a functor, but all functors are also invariant functors by nature of them being able to define IMAP, which is an invariant map, simply by ignoring this G parameter right here. And the same goes for contravariant, right? So contravariant also extends invariant, but in the opposite case. So we also override IMAP right here, but we don't ignore what we call G here. It's called FI. I don't know why. Maybe F inverse. That would make sense. But we ignore this first parameter here, this first function. So yeah, so much for that. Right, so invariant semigroupal just extends semigroupal with invariant, doesn't really add anything. You can compose it with apply. But these things really come in handy when you have to write things like codecs. So like most of the types we encounter in quote-unquote real life are covariant, right? Like list, like IO, like map, or I don't know, vector, option, either. Pretty much all of them, they're all covariant. There are a few exceptions, like reader, which is covariant in its, well, depends on how you define it, but if we look at something like Kleisli, it's in data. Kleisli, right? So Kleisli is both a covariant and a contravariant functor, depending on which one of these two type parameters you choose, right? So it is covariant in B, but contravariant in A, and that actually makes it, well, people call it profunctor, but I'm not going to get into profunctors because I feel like I'm already explaining a lot, and people want to see me actually work on stuff, or at least I want to see myself work on stuff. But yeah, so basically we have these different kinds of things where semi-groupal allows us to combine two things, two type constructors, right, within a tuple. And then we have what I called invariant add semi-groupal, which has the same thing, except it uses either instead of the tuple. And those two are basically at the root. And then from up there, you get all the way to decidable on the covariant side, and decidable on the contravariant side, and alternative on the covariant side. And I created a ticket for this like almost 2 years ago. No, it's been a while, definitely though. Let's see if I can find this quickly. Cats move by. Invariant superclass of alternative and decidable, right? So basically, let's say you have some kind of codec and you want to derive new codecs from it, and codecs tend to be invariant, right? Because fundamentally you have decoders, right? So decoders basically take some sort of representation, sometimes a string, maybe a JSON, maybe some binary protocol, and then they turn that into some kind of A, right? And so a decoder of A is a way to go from whatever protocol representation you have to that A, right? So if you have a decoder of int, that basically just means you can go from, let's say, string to an int. And if you have an encoder of int, that means you can go from int to string, where again, string is not fixed by any means. And what that basically means is that decoders are covariant because we return something from them. So like if you don't have an intuition for co and contravariance, you can kind of think of it as like consuming and producing, even though I think that like intuition has some leaks. But yeah, so basically you can say that covariant things produce something, or like they come out of it, whereas contravariant you have to put them in, kind of. So, and again, encoder, you put in a type and then you get out some kind of string, whatever representation, and decoder, it's the opposite. And if you put them together, you get a codec, right? Basically, you get a codec of some type A, or codec of int in our example, and that gives you a way to decode and encode. But because the decoder is covariant and the encoder is contravariant, that means the codec has to be invariant. And alternative are really nice for like parser stuff. Decidable is like the opposite for, it's really helpful for stuff like, like encoder combinators. And then invariant, whatever we call it, the superclass of alternative and decidable, is basically what you can use to work on the raw codec, not the raw codec. I don't know why I said raw. But yeah, so that's what we have, and I kind of sketched this up and I made this crazy looking diagram. So basically what we have on top here is functor invariant contravariant, and then we have the two different semigroupals, invariant semigroupal and invariant add semigroupal. And this one again is just an invariant functor that also has the ability to put them together into a product, and then add semigroupal, which I'm really not a fan of the name, but it's just what I have right now. If anyone has a cool name for this, I think maybe like someone suggested choice or something, which I kind of like. Yeah, and so basically what's in cats right now is only the product side of this. So we have invariant, invariant semigroupal, invariant monoidal, applicative, alternative, apply, functor, contravariant, contravariant semigroupal, contravariant monoidal. And then what's missing are invariant add semigroupal, invariant add monoidal, invariant semi-ringle, which I called this superclass of alternative and decidable. And that comes from the fact that product types and sometimes form a semi-ring, kind of, or a rig, depending on the definition. And that's something I won't go into, but if you're interested in why the hell that's that name, you can watch my talk, Monoids, from Scala World last year. Or actually, doesn't really matter. I also gave it at Scala Love. Alright, so we have all of this stuff, and we want to add this side of it to get to decidable. And I wrote a PR for this about, November 2018, so 1.5 years ago. But we couldn't actually ever actually look at it because in 2.11 there was a binary compatibility issue. But since we dropped 2.11, we can actually do this now. And I recently merged this code with master. And now it actually compiles fine. But there are some kinks we need to sort out. So for example, where do we even start? We might have something like, so one issue that I found is that there is already a method named sum on semigroup K. I don't know if that's an issue per se, but that basically means we might have like an ambiguous syntax situation going on. So if you look at sum right here, this is the same method, it just needs a functor. So if I then take this invariant semigroupal, invariant add semigroupal. Oh wow, this is really slow right now for some reason. This is also called sum, and I think we might have a clash here because at the end, alternative, as we saw, will extend both of them. And so what I had to do here in order to actually implement this was call this the monoid K thing, the monoid K method, with itself as the implicit evidence. So I'm not sure if we should just rename this thing. The other thing is that basically I had to add this new I nothing trait, and I stole this name from FS2. And I think actually when I wrote this back in 2018, I nothing had a very different definition than it has today. So okay, I must be in package. Oh shit. Where is I nothing? Definitely exists somewhere here. I know that the guys did something to make this infer better. Okay. So it's basically just, oh, interesting. Alright. Yeah, I'll try that. Why not? So if we look at cat's data, because the way nothing works in Scala is that it tends to, once you infer it somewhere, you get some weird warnings, and you get a lot of, I don't know exactly what the inference problem is, but there is definitely some issue there. Also, nothing is in Scala is the only thing that is poly kinded. So if it can infer, for example, a contravariant f, which is a type constructor, it will also use nothing there, and that is the only time you can use a value or a type in a position where it expects a type constructor. It's also an interesting thing. So I'm going to look at the package Scala of cat's data, and I'm just going to define this I nothing right here somewhere. And then I'll have a look at what we had before. Oh yeah, before we just had this sealed trait, and basically what the only thing it did is just exist, so it doesn't have any cases, right? And therefore you can never actually instantiate this outside of this file because it's sealed, and that means because there's no instance of this in this file, that means basically it doesn't have any instances. But and I think, I don't know if I copied this, but I definitely looked at the FS2 implementation back in the day, but maybe I didn't. I don't even, it's so long ago. So we'll just do something like this. I wonder if this will, we'll see. This will throw any weird errors. Yeah. So what's this? Trait, I nothing. There is no trait. Oh, is this? Yeah. This is just, didn't realize I deleted it yet. So I'm gonna go to core JM and compile this. Yeah, so this is what I meant, dead code following this construct. So it basically warns you when you have a it warns you when you have a value of nothing and use it, which we kind of do here. But this absurd function basically just allows us to take nothing and turn it into anything, any a, because if you have a value of nothing, that basically means either you're throwing an exception or you're doing some kind of as instance off, but you can't have a value of nothing. The same way you can't have a value of nothing. Like, that doesn't even make sense semantically, linguistically. And so basically what this does is just, if you were actually to call this with something, it would just, recurse endlessly. So what we're just going to do is just going to throw an exception. Throw a new exception. Somehow instantiated a value of I nothing. This is a bug. Please report it to. I don't think actually. If we ask to report this to type level cats, that won't really do a lot. Because whoever used this or supplied it in their library, I'm just gonna leave it. This is a bug. Okay. Not the prettiest thing, but this is totally safe just because you can't actually call this function. And yeah, so let's compile this again. So the reason we need this is because nothing is the identity element for either, right? So if you think about it, if you have, like, if you look at the definition of left, Scala util left, oh, interesting, okay. Never mind. I thought this was typed like this. But it is not. So my point is it doesn't really work here. But that's okay. But basically that is the gist of it, right? So in if you just do something like this, what the Scala compiler will infer is a left of int and nothing, which is the same, which is, you know, a subtype of either int and nothing. And this means that if we have any value of either int nothing, that means this is basically isomorphic to an int, right? Just because there's nothing on the right side, no value that we could possibly have there, so it must be the left side, and therefore it must be an int. The same way, if you look at something like a tuple of int and unit, God, I can't type. This is also isomorphic to just an int. And that's just because this unit doesn't add any value. And isomorphic just means you can go from one to the other without losing information, right? So you could go from this to this and back again a million times, and it will always, the values will never change, right? And that's basically what isomorphic means. And in the case of applicative, when we do something like semi-global of f dot product, and we have some kind of f of a, and then we have f dot unit, let's just say that, this must be isomorphic to fa, right? So this is just the left identity law, or the right identity law. It's one of the identity laws. And this is the same if you like look at it from a monoid perspective. This is the same, like a lower kinded. This is the same as saying a plus. Well, I can't type today though. A plus empty must be, again, we use this thing here, must be A, right? And the unit is the identity element or the empty element, and that means things must stay the same. That's the only law you have here. And yeah, so with tuples, unit is that kind of identity, so even though the type here is going to be f of a comma unit, and the type here is f of a, because we have this kind of isomorphism, this is still a valid law, right? And the same thing we can do for some types, right? So we say, I guess we call it invariant, whatever. So we'll just call it sum of fa and f dot void or nothing or something, which has type f of, or I guess I nothing. We'll just use it there for better type inference. Even though this is all pseudocode, this must be by law the same as just f of a, and this will have the type. And this will then have, because we use either here, this will have type either a or nothing. And again, because of this isomorphism, we can also compare these two. And yeah, so if we look at the actual laws defined for this, I call them invariant add monoidal laws, right? should this be left nothing? Yeah, it should be. I messed this up. Basically, I define these two helper functions right here, left nothing and right nothing, and they basically just say that, oh, this is the same as this, and I can go back and forth, and this is the same as that. And the only thing I'm doing here is folding using this absurd function, which turns any I nothing into an A. Dead code following this construct. Well, that's annoying. I wonder if we can somehow make that shut up. I guess that's why we had the seal trade in the first place, because of issues like this. Right, but basically, these are the left and right identity laws that we have for any kind of monoid, and this add monoidal is just another form of that monoid. Yeah, and then if you have an invariant add monoidal and an invariant monoidal, which again has the same laws, except it uses product and unit instead of sum and zero. Call it zero. I don't know if that's the best name, but I kind of like it. Then you can go to a semi-ringle, or what basically is the supertype of alternative indecidable. So yeah, this doesn't work because of the dead code. Oh, that's so annoying. Something like this help? Probably not. Oh, okay, so now the dead code is in there. Might have to change the. Wonder. Need to ask Mike Pilquist and the FS2 team how they deal with I nothing, to make those errors go away. But yeah, so basically, semi-rings have this absorption property where you can kind of think of it like, like multiplying by zero, which is basically what it is. You take the product of something with zero, and that's always going to be zero, no matter what you do with it. And then distributivity is basically that products distribute over sums, or other way around. I never know. I always mix that up. And we can kind of prove that by saying that either tuple AC and tuple BC is the same as either AB, or either AB and C, and we can go the other way around. Yeah. So these are also isomorphic, and then any F that has an invariant semi-ringle in scope also has to do that. Why do I need to do this? I wonder. Must have thought something about it at the time. What? Does it even matter what I do here? Can I just do it as instance off? That's still... Okay. Will that stop the complaining? Dead code following this construct. Okay. Yeah, I need to somehow deal with that. Let's turn off the warning. Dead code warning. Where's BT? Oh, I wonder if it's even in here. Scala, fatal warnings. Is it dead? Y1 dead code. So yeah, we'll just uncomment this for now. Yeah, we have to like build this crazy thing of Scala flags, Scala C flags, because we have all these different versions, and it's cross-compiling. But yeah, we have a Dotty build working on master, which is pretty neat. It just requires a lot of stuff, so I have to reload this, which takes a while. But yeah, so let's see. Sorry about that. So I have a bunch of this stuff that's pretty much almost ready to go. I think I must have. I wonder if I wrote some test code for this at some point. Invariant. It was like a CSV codec or something. Shit. CSV. Oh, that was in the docs. Do we also have it? No. So yeah, so a CSV codec is basically something that can read from a CSV, which is a list of strings, and return maybe an A, an option of A, and some more CSV, and it can also write any A into a CSV, which is that codec type we kind of talked about before, and this is invariant, and whoever wrote this docs, Olivier, oh, I didn't know that, 4 years ago, damn, time flies. I don't think that's true. I remember when this happened. I don't think this is 4 years ago. I don't trust this. It's probably rounded up. Oh no, I'm wrong. 2016. Wow, that's really a long time ago. Okay. Oh, it might have been invariant semi-Google that was added when I was already part of CAT's maintenance. So basically what they do here is let people where is it? Okay, no, I can't find it. Terribly prepared today, I'm sorry. But we could define this for any codec. So for example, for this one, we could definitely do that. Where did it go? Why is it not under reasons? Okay, it's right here though. For CSV codec, we could define an invariant semi-ringle, and that would basically allow us to once we have like one thing for a string and int, that would allow us to derive them for any product or some type that uses a string and int, just by using the functions provided, which are called, sum, product, and IMAP. And that's basically all we need. Okay, so what we would like to do is to have this extend invariant admonoidal. But the problem there is, of course, that semigroup K itself is not a functor, even though I think there's almost no semigroup K or monoid K that are actually not covariant. This is just because empty for all A's. This is basically, for covariant types, this is the same as saying nothing. Because if you think about it, if you have an f of nothing, you can just call map on it and do like nothing dot absurd or I nothing dot absurd, and that gives you any type, right? So you can turn nothing into any type. But for the contravariant case, it's not as simple. So if we look at contravariant add monoidal, it basically goes the other way, right? So where with empty we gave it a function, right? We said empty dot map f or I nothing dot absurd, which goes from I nothing to a. But remember that contravariant basically means we flip the arrow, so we go from a to I nothing, and that means that we have to have this weird thing instead of the nice thing we had before. But yeah, the good thing is we can define this in terms of 0, right? Simply by contra mapping on this. I don't know if we even need this, if this does anything, but I think the only reason I did put it in there is because this comes from Haskell, right? So a to void, which is nothing in Haskell, to f of a, which is the same as this. So I don't actually see a lot of utility with this, but it does kind of, maybe we should just delete it. Maybe this is just here for, but yeah, I'll think about it. Maybe one of you wants to tell me, oh yeah, this should definitely be deleted. And yeah, and then we have contravariant add semicolon, which is the decidable here, right? No, it's divisible. I'm sorry. And yeah, and then decidable is the thing that I don't have in this PR because Steven Lazaro actually did have a PR for that up here somewhere. Oh, yeah, I think it was him. Yeah. So he made a really nice PR with a bunch of instances and all of that stuff. So decidable with some and decide chosen 0. What is trivial? What is that come from? Oh, trivial is from. Oh, interesting. Yeah. Yeah. So basically, he did this and added for something like const, which is probably something I would need to do. IDT. Kleisli is definitely decidable. Nested. It's a lot of these instances that you can define, like for example with const, right? Const doesn't really have a lot, but you can give it instances if the underlying D here has stuff. Oh yeah, this was an interesting discussion. I remember thinking about this and coming to a conclusion that I was very wrong about how I thought these things. And this guy, Catastrophe, who is, I think he just basically told me I'm wrong here, and then it took me like a day to realize how wrong I was. Yeah, back in November 2018. Wow, feels like forever ago now. But okay, let's actually implement stuff. So we got rid of that flag for now. Just want to see if this compiles. And what we should do is rename this sum. I'm gonna rename it choice because I called this thing choose. No, I called it decide. Yeah, because sum is already a thing for semigroup K, and we want to keep that. We want to keep that name. Unfortunately, backwards compatibility is everything, and I don't see it. unless we somehow skip the syntax generation for it. But yeah, I don't see how those two can be there together without causing any ambiguities, unfortunately. So we call this thing sum, which means in alternative, yeah, we have to call this choice as well. Or maybe we should call these things contravariant choice and I don't know. Names are so hard. I really don't even know. And then I'm just gonna call this sum like that. Let's see. For all the laws compile. Yeah, it's taking a while. Is there any questions or something I can clarify in the meantime? I feel like I'm talking a lot of abstract stuff here, and I can totally understand if this is I don't know, maybe you need like a visualization or something. I'd be glad to help people understand specific things. But yeah, let's actually look at something that's been in cats for a really long time, which is contravariant semigroupal. And contravariant monoidal, more like. So right here you see, and this is the cool thing about the duality, is trivial, which looks exactly like monoid k dot empty, right? Given any f, I can give you an f of a. And that's just because contravariant monoidal or invariant monoidal has this unit, which just gives us an f of unit. And if we contramap that, we can basically contramap it to any type we want. Oh, I need to fix all the laws. Okay. Oh yeah, I need to fix everything. Oh shit. Okay. That's not too bad. And that's kind of the really interesting duality here, is that on the covariant side, if we use product types, like with applicative, if we use sum types, like with either and monoid k, we get this sort of construct. And on the other side, if we have contravariant monoidal with product types, then we also get this same signature. And I don't know exactly what this means, but it kind of like really shows the duality of, you have covariant and contravariant functors, which are like one part of the duality, and then you also have sum types and product types, which is the other part of the duality. Yeah, and then invariant semi-ringle basically takes all of those into the same thing and places it solely kind of in the middle, where it's not both covariant and contravariant, but that's false. It is neither covariant or contravariant, but it is both. Well, it's not both a product type, but it is both capable of combining things within product types and within sum types. But yeah, why is this defined so weirdly? Abstract trait invariant. That's. Why would metals do this? Oh, now it's fine, huh? What changed? Oh, okay. Just fix itself. Alright, so let's fix those laws. And then yeah, let's just go right here. So this is right. And then this is unfortunate. I kind of like this sum and product naming, just because it very explicitly says, oh hey, you combine two things within a sum type, and product combines two things within a product type. But alas, I can't always have nice things. So, and this is just associativity, right? So if we take these parentheses right here and we move them to around FA and FB, then those things have to be the same. That's associativity. This is choice. Oh, and the reason? No. Why do we... Oh, this is just for the IMAP stuff. Gotcha. So, I'm going to try to compile this. I'm going to go to the bathroom real quick, and I'll see you all in a bit. Alright, I am back. And in the meantime, it all compiled, which is really nice. What are you looking at here? Oh, okay. Contramap some right distributed. Ah, right. So, in addition to laws I talked about earlier, which are just associativity and identity, we also want, I guess we should rename this that. We also want our combiner functions, product and choice, which we call them now, to distribute not just over each other, but also over the mapping, right? So, for example, you had some kind of f of a, and you map it with. Wait, where am I need to figure out my own intuition. So something like this, and then doing something like okay, I'm not sure. But we can read this right here. It's not too bad. So basically, if we contramap them both and then call choice, that should be the same as contramapping. Oh, right. So it doesn't matter if you first call choice or contramap. Yeah, as long as you, and then yeah, okay. So basically, given something like monoid K, what we would want is that FA map F combined with, or combined K'd with FB map B map G. That should be the same as calling FA FB, and in theory this wouldn't work because these are different types, but let's say instead of this we have our choice function, choice, and then taking the whole thing and then mapping it using something like bimap, because that would return an either, and then we map the left hand side with F and the right hand side with G. Yeah, and so this is basically what this is, just with contra map instead of map. Do we have those same laws for invariant at semigroup though? So I think we should probably have them, if that even makes sense though. Maybe it doesn't. Okay, so just that. But yeah, let's try. I guess I need to rename all of these. Choice IMAP distribution. So given some types here, we have an f of A, an f of B, and we also have a lot of functions. We have f, which goes from, oh god, how many did I use? So I use different types here. Here's C. Alright, yeah, we can do that. Sorry for switching around so much here. So, so you have F, which goes from A to C, and then we have G, which goes from C to A, and then we also have H, which goes from B to C, and then we also have HI, I guess, which goes from C to B. And then what we'll just want to do is say the choice of FA and FB IMAPPed. I'm going to import the syntax. Import cat syntax invariant just to get this IMAP syntax. So now we basically have, so this gives us something where you go from either AB to B and B to, oh, and so the reason we can't do this is because, oh no, we can't do this. We should be able to, can we do this? Oh, B is just some other type here. Yeah, I wonder though, if this makes sense at all. What's the error here? Yeah, but let's just try to see what happens. So the first thing we have here is we go from either AB to C, which we can do just by saying fold. If it's an A, we go to we call F, and if it's B, we call H. And then the second function would have us go from C to either AB, which we can't do because we'd have to arbitrarily decide which side to go on. So okay, this law is out. So there was a good reason not to include this law, which is good. My past me did something right. But yeah, that's pretty nice. I wonder, did I ever add any instances to this PR? Let's find out. Laws. Doesn't look like I did. Okay. So this is something we'll have to remedy. So we can start with something like let's see, what do we have? Syntax. Something like, so it's invariant, but doesn't, do we even have anything invariant here? Isn't that fascinating? We don't have a single invariant data type in here. So I guess most things are already either co or contravariant. Is set invariant? Yeah, but we don't give it that type. Is set defined as invariant? Yeah, it is. Is that the same true for sorted set? I wonder. The thing is though, sorted set, the reason we can't give it any kind of functor, not even an invariant functor, is because it requires an order. So we can't just call map on it without also requiring an order for that different type. Alright. So what we can definitely do though is define instances for something like const. So const is a very interesting type. It has like a billion instances that are all defined inductively. So if we have an order for A, we can define an order for const. If we have a semigroup for A, we can define a line. If we have show, we can define show, on all these kinds of good stuffs. So yeah, so here we can see you can have a contravariant monoidal if it has a monoid. And what we could do right here is, for example, just add a contravariant. Oh, well, those can't put it in the same scope though, because they both extend do they? They both extend from the same root, but that should be the same here. Commutative, duplicative, and contravariant monoidal both extend invariant. Which is odd to me. Why would they be in the same? I put this here. That's even more interesting. Migrate to new. Oh, okay. I put that line there. And Travis. I'm confused. Oh well. So traverse, show line. Oh, actually, the good thing about all of this is that we use the so-called scato encoding, where we don't even, because of exactly this reason, because of the ambiguities and the shared roots. So contravariant add semigroupal doesn't even extend contravariant, it just uses it as a member, which makes things a lot easier for us in this case. So we can definitely just put it right here if we wanted to. Yeah. Cats data contravariant add. God, that's a horrible name. I'm sad no one's come up with a better name yet. Contravariant add for const d star. Contravariant. So what we'll need here is choice and 0. So the good thing about this is just const of empty. Mono d dot empty. What's it's missing. Oh yeah, just talked about that. Ooh, why you gotta do me like that? Metals, why? So this should at least compile. Yeah, and then this is just cats data contravariant for const. Cool. And then this choice right here will basically just say that we are going to combine fa get const and right. So this gives us a d, and then we're just going to combine it with this other d. It doesn't work for some reason. Oh, look at this guy. Whoever did this. He got it right. He got it figured out. You can just retag it and then use the combine function that's already on there. So retag it as either A, B, and then combine it with the retag of this one. And that should do the trick. Cool. Oh, let's fix this. This is not called choice, right? Distributivity. This is called choice associativity. Maybe we should just call it invariant choice as a type class. Is that a good idea? What do you guys think? Okay, so it's compiles. Let's go back to const. So we have all this stuff. What about invariant? Does it not have invariant instances at all? I guess it doesn't need to. Ah, yeah, fascinating. Because it can always be a contravariant. Right, so in this case, I wouldn't even need this if we had decidable, which we don't have yet. Oh well. Okay. That's okay. That's okay. This is still good. We should check the laws for this. So we'll go into const tests. Oh, we don't have any contravariant admonodal. Oh, that's annoying. How does this even work then? Okay, yeah, this is what I thought. So what we'll do here is we'll just reuse this and use an actual, create an actual contravariant admonodal. Create an actual instance of this type class, which we haven't done before. Not just an inductive one. So contravariant for predicate. So we will. What happens if I do this? Oh, that's actually perfect. That's exactly what I want. So in the 0 case, what we want to do, and here again we see kind of the duality, is that we basically just want to always, no matter what happens, we will want to return false. And this is just the one contravariant. This is just this. Don't have any scope. Maybe it doesn't matter. Will this work? Yes. Excellent. Oh. Dead code. How is this? Oh, right. I didn't reload metals. I only reloaded SPT. Fine. So because some types and product types, they kind of go hand in hand with like Boolean logic in a way, where nothing is kind of like false, unit is kind of like true, and is kind of like a product, and sum is kind of like or. It kind of works that way. But it also, as far as I know, it also works. You can also just flip it because the kind of, does that work? Oh, maybe no. No, actually, I don't think that's true. Disregard I said that. Or try. So what we're going to do here is the dual of what we did up here, which is we're going to run both of these predicates. Which gives us a boolean right here, and we are going to, oh, actually, never mind, we can't even do that because this x right here is an either. Oh, this is the exact same thing I got wrong the last time that I talked about earlier. So in the case we have a left a, what do we even do here? Oh yeah, we just call fa with that a. In the right case, yeah. This is very mechanical, actually. I don't think about it. Do you need to call run? Yeah. It's not apply, it's run. But that gives us a boolean either way. And then that's it. And then, yeah, so what I said about and or is still true, but it doesn't directly apply to what we're doing right here. So now we have this thing, and that means we can define, we can do a check all for the contravariant admoidal for predicate. Contravariant admoidal tests of predicate. Contravariant admoidal. Let's just use boolean. And now, if we actually test this, so we'll do test slash test only. Why? Oh, it's a tests JVM. Yeah. Cool. Yeah, they autocomplete. We'll only run this contravariant suite right here. And then we'll see what happens. How come nobody's texting in chat? Is no one listening to this? It seems I have 6 people online. Maybe you folks are just a bit shy, which is totally fine. Okay, it's taking a while. But yeah, like the combination of these two things, having unit, product, choice, and zero, that is what decidable basically is about. Oh, look at this. I did find the codec thing, which is cool. What is that? Mini list. Oh, this is just so it doesn't blow up like crazy. Yeah. Mini list of boolean. Oh yeah, this is a binary codec, so basically it allows you to read binary things using a mini list of boolean. So it's the same kind of codec that we had before, where we read something in from this little binary thing, get an option of A. Listening and listening. Thanks, Lance. I appreciate I appreciate you commenting. Let me know if something about this is unclear. And then, yeah, and what we do here, what I assume we do here, oh, we define, yeah, we basically define an invariant monoidal, but what we're going to try to do is to define an invariant semi-ringle. God damn it. Why? I don't want to. Let's get rid of this. It should be fairly easy. And if we can't do this, then something's definitely wrong with our code. So that would be good to know either way. So I'm just going to stay in the same style and going to create a cc0, which def0 is going to give us a bin codec of I nothing, which doesn't seem very useful, but I guess neither does this. Like, why do we care about writing and reading unit? But you know, so this is a new bin codec for I nothing. And then we'll just need to implement read and write. So if we want to read and return nothing, this will always be none, right? And we'll just return S because that's kind of all we can do here. Because you can't actually read nothing. That just doesn't make any sense. And in the write case, if we want to write it, we will return an empty list here, or an empty mini list. Because yeah, we can't write anything. That doesn't make any sense. So that gives us cc0, which is not very interesting. But cc, I guess, choice, ccc, it's going to be a little bit more interesting. Where we're going to combine two bin codecs. So we have the tests pass, which is awesome. So given a bin codec for some type A and a bin codec for some type B, give me a bin codec for the sum type of those, which is either A, B. This is gonna be fun. Like, I'm looking forward to this. But oh, I need to do new. Yeah. So now read gives us this, and write gives us this. So the write case, I think, is a bit easier. We basically just pattern match, and if it's a left, we use, this is an A, right? We'll just use this codec, right, to write it. And in the right case, we get a B, and we use FB as our codec, or as our encoder. And in this case, it's a bit different, I think. Yeah. So what we'll want to do is we'll have to apply these codecs one after another. So what we'll do is we'll say if FA can read this thing, right? So given a binary thing right here, so yeah, let's just use some curly braces to untuple this thing. So we have an option, which I'm just gonna call fuck it. Sorry. And bin. And if this works, right? So if we read from this, oh, actually this is just an option of A, right? If this works, and this option is a sum, then we don't even have to try this other one. We can just say, hey, yeah, sure, we'll just use this one. And so this basically means we are left biased in a way, in a very different way than, for example, either flat map, but it's kind of the same idea where you go from left to right and apply things left to right. And it's kind of like the or else semantics that we actually saw with combine K. And of course, choice is a specific version of combine K. So that would make sense. And combine K eval is what we implemented it, I think 2 weeks ago, 3 weeks ago, I don't know. So in this case we have an A, and we're just going to then return a sum of left of A and the rest of this. But if we can't do this, what we'll do is we'll have to try to read this with the B codec, the B decoder. So in this case, we'll use just S again, right? Because well, I guess if this didn't succeed, this bin and S should be the same, but let's just read S for safety. We're gonna read this, and that's going to, I guess, return an option of B and some kind of okay, never mind. No, I kind of need to do this. Yeah, namings are hard. So, and what we want to return here is then just basically ob.map, because this is an option of B and we need an option of either AB. So we're going to have to do something like this, and then return the into. So what I would like to know, and then we'll just mix those two in, those two with TC choice and CC 0 and require invariant semi-renal. So I want to see if this compiles at least. Yeah, that will compile because there's no sources in test JVM. They're all in test. Okay, cool. Awesome. Dead code, yeah, whatever. All right, so what we'll now be able to do is actually test the invariant semi-renal. I want to say laws, yes. Right, semi-renal tests. Do we need to import these? I assume so. Yeah, so let's just use this thing. Okay. Don't need these. Right, and then we want that invariant semi-renal. And the same goes over here. And this checks that this is a valid monoid and that encodec is a valid semigroup. Okay. Why not though? What? It's right here though. Why would it not find it? Oh, okay. So what we need to do here. Oh, this is. Yeah, I'm just gonna put it right here. So the fact that this doesn't work makes sense to me. How do we do that? Wait, what did I actually change here? Am I? Yeah, that looks good. Okay, this will work at some point. So what we need is to check if two bin codecs of I nothing are true, and I'm going to claim that they're always true because you can only have a single bin codec for nothing. That makes sense. Bin codec nothing equals EQ for bin codec of and that one is going to be EQ dot always true. Shit, what is it called? Oh, that's the type. And then all equal. There we go. This doesn't make any sense to me. do we not? Oh, actually, we so if we look at this one, we have this add type class trait, and for those of you that remember this, since we're trying to, or that since we're cross building to Dotty and macro annotations are no longer a thing in Dotty, that means that we switched over to a Scala fix solution. And so this object right here, def apply, which takes, this thing is no longer being auto-generated. So implicit evidence of invariance signal of f. Invariance signal of f. Where we could kind of implicitly summon this. This is being generated by, this would be generated by ScalaFix, which I'm going to run in a second, but let's first focus on this. So now, this should call this apply method right here. There we go. So let's try to run this. This thing is called the bin codec invariant modal suite. And hope it works. And I guess we should rename this. But yeah, let's see what happens. I'm kind of, I mean, I hope this works, but who knows at this point. What I would like to see is the difference between CC0, which just always returns, oh yeah, it always returns none, and an empty list. And unit also returns an empty list for writing, but always returns a sum here. I think that should be fine. Okay. Yeah, and we should probably rename this whole class to encodec invariant semi-renal suite once we're done. Oh, I love this. How did I not? Oh, okay, so that's bad. Failing seed, yeah. When past stuff expected. List false. Oh god. This is horrible to read. Expected something like that, and what we got was CC IMAP anon. Well, that's unfortunate. Why can't we? What does the EQ look like for this? Yeah, I don't understand this. EQ by read, EQ end. What is this? Wait, is this part of that expression? Oh no, this is, I'm sorry. This is a block. I thought this was, okay. So these should be the same if they're right. And those should be the same by reading. Oh geez. Yeah, I guess I'd have to like dig into this. This is already the shrunk version. God damn it. Good thing is we have left identity, but not right identity. Wonder if we, okay, so there's more stuff failing here. Right distributivity doesn't work. Oh Jesus. Yeah, I'll have to clean this up and figure out what's actually the issue here, because this is not easy to look at. But what's weird here is that, oh, because we don't have a toString defined. Yeah. Yeah. God, that's going to be really annoying. What does this do? Oh. Yeah, I don't feel like debugging this right now. I've already spent most of my day debugging something I didn't want to at work. But yeah, what else could we do here? Let's see. What else needs to be done? So maybe this is something I can't even tell what the problem is, just because it's so dense with information that I don't want to see. I wonder if it's something about this, because it irks me kind of that writing with nil would be the same as writing this. Maybe this is wrong. I'm not sure this is right, but even then, that doesn't explain why this would fail. Right identity. So if you combine a codec with I-nothing, it should stay the same. Oh. The right part? Wait, so how do... Let's think about this. So if I do choice, and I write, yeah, I don't know. This seems right to me. Like if you read something, right, and it tries to read this first, it will return a none, and therefore it will go into this case and try to read it with the right one, the right hand one. So that should work in the right case. If I try to write something, it will return an empty list, and then oh wait, so if I have an either AB, okay, so maybe it's something about this. No, I'm not so sure if this is actually correct. I'd like to try this. Maybe we should just go into the console. Yeah, let's try this. Let's see. Console, tests JVM/console. So, is all this, okay, so, hope this is in scope. Cats, tests, oh shit, no, I know why. This should be test console. So now if I do bin cats test stuff, encode it, yeah, okay. So we'll just run to import, I guess, everything that's in here. Can we even do that? Okay. So now we have this thing, and what I want basically is to check that if I write some kind of either AB, so what do we even have here in scope? We have a bin codec for what? We must have it for something, right? I guess we have, oh, we just kind of, that's interesting. We generate the codecs. Fascinating. Okay, yeah, but why not? So How does it, shouldn't we have a codec and then, I don't know. So let's just write a codec for something like int. Why not? Bin codec for int. And to read an int from a list, oh, that's annoying. So def read from this bin thing. It's going to return an option of int and a binary thing. And to do that, pretty sure I saw somewhere it was 2int or something. No, not in there. 2int. Oh, that's mini int. Is there a way to turn binary into an integer? It must be, right? A2 bin. What is this? Okay, oh, that's just that. Okay. Int dot. Does anyone know? Please put it in chat if you do. Damn, that's annoying. I guess what we could do, would that be a valid codec? Yeah, you know what? I'll just make this simple. By doing something like, so if we read this thing, we'll just read the whole thing and we'll just return the sum of read the whole thing and we'll just return the lengths of that list. Which is not what a real codec would do. And then here we return mini list dot empty. And then when writing such a thing, we need to make sure that these are actually compatible. So when we write an integer, we want to get a bin, and we'll just use a how do I create a mini list though? Oh, I guess I can do mini list dot unsafe. List dot, isn't there a repeat or something? Shit. List dot, so I can do list dot range 0 to n dot map true. How is the binary represented? Strings of 0 and 1s byte array. Yeah, it's a mini list. A mini list of true and of booleans. So it's really annoying. But I think this should work. Let's see. Oh no, I fucked it up. Let's try this again. This is the read thing should work, and then the write thing. Just misspell the so s.toList gives us a list of boolean, but in my case I don't even care what's in the list. Basically this is a very dumb codec that doesn't really do anything. So we can try this. res1 dot what's the function here? So if we read from our mini list a list of true, that should give us 2. Yeah, some 2 and then an empty list. Cool. And then if we were to read that, write that, sorry, if we write 2, that should give us that same list. Yes, excellent, cool. So this is a somewhat valid codec for some definition of valid, and the right identity law, let's just check that real quick. Right identity law, no, it's in invariant, it's in laws, of course. So the right identity basically means that if we choose something with 0, I know a quick way. Well, I already wrote it, Pedro. Too late. But yeah, if you do, like, we can totally do that. I don't think it will really matter. If we can even replicate this bug. So now what we want to do is we basically want to create a bin codec of either and nothing. So what we're going to do is we're going to call bin codec dot cc choice. Oh shit. Okay, now we're gonna call bin codec dot bin codec is invariant semi-ringle dot choice with our int codec, which is res1, integer parse int binary string. Yeah, but I would need to, I guess I can turn that list into a binary string. That shouldn't be too hard, but I'm gonna try without it for now. Bin codec blah 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 is 0. So what kind of codec will this give us? An either of int and nothing. And now this codec, because we use it with 0, should be the same as res1, right? Isomorphic at least. So when we call res4.read with the same argument, it should give us something isomorphic. Sum left 2 mini list. Yeah, so that the read part is fine. So let's figure out the write part. So if we write with a left of 2, what happens? Should just write that. Yeah, that's the same. Maybe it's the wrong order. Maybe what we want here is to do, or maybe there's a bug in this thing here. That's totally possible. I don't know what the hell this does. Creates some random stuff and does something. Do we even know? Does this really? Well, I don't know. But yeah. So we'll just do the other way around to see if that also does the same thing. That gives us, again, 2 with an empty list. And now if we write a write of 2, you also get the same thing. So yeah, I assume the bug is somewhere in this bin codec generator, which is kind of like sketchy to me. Like, how can we possibly generate binary codecs, like random binary codecs? Just, yeah, I don't know. I guess I'm gonna have to look into this. But yeah, I think I streamed for long enough. Unless any of you have some kind of questions, I think I'm gonna call it a day or a night. Finish the stream. I hope you all enjoyed this somewhat, even though it was very, I think this was like probably my most abstract, most explainy kind of stream. But yeah, let me know if you have any comments, questions, whatever, and if not, I'll just end the stream right here. But yeah, at least we kind of proved, or we didn't prove, but we took one case and made that true. I wonder if this is true for other stuff, but we'll have to see. Okay, thanks everyone. Did I need to actually turn this off? Oh look, that's me. Wait, how do I turn this off? I think usually I just kept it open. Lance has a problem. Fun to watch someone familiar with the code. Yeah, that's the whole point. I'm very glad you liked it. Yeah, thanks again for tuning in. I'll see you all soon.